This is the first of 6 parts in Module 1. And the question is, what is mechanical earth modeling? A mechanical earth model is a model of the mechanical state of the formation of interest. So here I show a realistic formation. So it's not a typical shoebox model, so it's not a regular cuboid. It could have layers that could be dipping or sloping. You also see there are several faults or fractures in the domain. And that basically represents the structure of the reservoir, which is the reservoir geometry. And that's part of the components of a mechanical earth model. So the reservoir structure or geometry is one of the components. The strength of the rock and the stresses applied on the rock. So we could be interested in, say, this brown layer here, but there are several other formations sitting on top of that formation of interest, and they have mass, right? The mass multiplied by the acceleration due to gravity gives you the force they exert on the formation of interest. And that force divided by the area through which the force acts gives you pressure or stress. So stress is force per unit area. So the force exerted by the rock mass sitting on the top of the formation of interest is the overburden stress, also referred to as the vertical stress. So we'll later talk about the different components of your stress, which are the vertical stress and the maximum horizontal and the minimum horizontal stresses. When those stresses exceed the strength of the rock, then the rock fractures, and if the rock mass moves across the fault or fracture surface, it becomes a fault. And we'll talk more about that when we talk about faults and fractures. The mechanical earth model also includes the material properties of the rock. And material properties include elastic properties, which are Young's modulus and Poisson ratio when you have linear isotropy. So those are some mechanical properties. These are also mechanical properties. The rock strength, UCS, is unconfined compressive strength. So unconfined compressive strength, it's also in units of megapascals. It's force per unit area. That describes how much stress the rock can withstand before it fractures or gets deformed, before the rock fails. That's the more technical term. There is also frictional angle, which is related to the frictional strength of the rock. So how much of load can the fault or fracture support before it fails? So typically in fractured reservoirs, there is a fracture there, but the rock is still closely confined and compacted together, right? And if you apply a very minimal amount of stress, there is no displacement. But when the stress applied exceeds the frictional strength of that fracture, then you could have displacement, even though you don't have the rock matrix like this solid part fracturing, but you can have movement across this surface. Your mechanical earth model also includes petrophysical properties. which include permeability, porosity, these are standard reservoir engineering stuff, fluid pressure, which is your standard reservoir pressure, and the failure criteria, which could be fracture toughness, the value above which the rock fails. The input to come up with this mechanical earth model could come from well logs. We'll talk about this. We'll work on a real example from the Volve field in the North Sea. Input data could come from seismic interpretations and seismic inversions. When you hear the word seismic, it's all about acoustic sound. So we send sound waves down to the formation of interest. It gets reflected back to the surface, and we measure that travel time. Then we take that data and we interpret it, and we can figure out the geometry of your reservoir. We invert it, we can calculate the rock properties. We also perform well tests, and we can get permeability and other values from your well test. We can also get cores while drilling, and we can take the cores to the lab and perform rock mechanics tests using like a triaxial testing equipment, and from that we get parameters like the Young modulus Poisson ratio and also the rock strength. You can also use numerical models to come up with inputs for your mechanical earth model. Here I show how we typically use mechanical earth modeling. So mechanical earth models can be applied to at these different stages in the life of a reservoir. Typically, we start out with some easily available data. It could be from analogs, so reservoirs that look like the one we're interested in. From acoustic data, which is typically what you get first during exploration. From the acoustic or seismic data, we can infer the rock physics, like I talked about in the previous slide, and the geological model. This will come from seismic interpretation. This will come from seismic inversion, and we create our first pass mechanical earth model. In the mechanical earth model, we have the mechanical state of the rock, which we discussed in the previous slide. So using this mechanical earth model, we start to drill. And while we drill, we obtain new data, right? So we can validate our model and we can calibrate the model to honor the newly observed data. So we update our model with our data. Then we start to produce from the reservoir. And during production, we obtain actual data. And we also compare the data with what the model predicted, and we calibrate our model. So our mechanical earth model gets more accurate as we proceed further in the development stage of your field. And that's basically the moral of the story here. If you have core data, you can also incorporate that into your mechanical earth model, because that's also hard data. You can get the rock strength, the the elastic properties, meaning Young modulus and Poisson ratio, which we talked about in the previous slide.